So we were discussing this PK reduction, and then I was telling you that the basic idea was that an infinite volume lattice was mapped into a lattice that contained only 4 matrices, just one side, right? So this is called the volume reduction. And to some extent, it's an instance of something that has been going on in the community for a long time, which is more general, even applied to continuum physics in some cases, which goes under the name of volume independence. And I don't know, people like Mithat Unsal or Kozum, Yafi have been also working in these things from a continuum point of view. So the basic idea is that the degrees of freedom that live in the group and the degrees of freedom that live in space are entangled between themselves, and well, they are mixed in such a way that you can use some for the others. No? So the main idea is that there is a kind of effective volume that contains both of them mixed, and then you can work with the effective volume instead of the original volume of the box to describe the physics and to probe the dynamics. So for instance, well, many cases, if you live on a torus of size, let me do Hamiltonian formulation, for instance. So you live on a torus, on a 3 torus that has periods of size L, and then R is the time. The effective volume in some cases takes this form, the size of the torus and then the n of the colors. Okay? So the idea is that maybe the dynamics of the theory is driven by this quantity instead of by the torus quantity. And one particular consequence of this idea is that if, for instance, now at L fixed you send n to infinity, the theory goes into the thermodynamic limit at fixed torus size. This is why it's called volume independence, okay? Because even if the torus is small, the larger limit gains for you the thermodynamic limit, okay? So this is basically the idea. So Eguchi-Kawai reduction is in some way a realization of that, where the lattice is, the torus is just one lattice spacing of size. So the torus would be this size, right? So you can do various things here. You can send n to infinity at fixed lattice spacing, and then you would recover the thermodynamic limit of the lattice theory, okay? But you could also think of sending L to 0 and n to infinity, keeping the effective torus fixed, and this will be finite volume in a box. Finite volume Lagian physics in a box.
Simple questions. If I take n finite but increase n, is it seen in lattice simulations that the finite volume effects are actually smaller as n increases? Or
this is what I will try to discuss. That there are some instances in which this effect has been checked. There are complications, but I will describe a case that we analyzed, that is T2 times R, where you see some of these effects coming in. There are problems, which are related to the problems that appear in Eguchi-Kawai reduction when you try to do it the naive way. So I'm going to discuss how these things appear.
The question was too early. Back to the Eguchi-Kawai, so there is the issue with Eguchi-Kawai that it breaks the real symmetry. But it really should not break any symmetry if it really describes QCD, where in infinite volume the Polyakov line has to be 0. So
yes.
How do I know? So if I didn't know what QCD describes and I didn't know what I expect, I might take Eguchi-Kawai and say that, oh, that's QCD. But it's not. So is there some way of figuring out of?
But why do you say I might take it and?
So you give me the Eguchi-Kawai model.
Yeah.
You tell me that theoretically that's the reduction, volume reduction of QCD. I look at it and I discover that in the strong coupling it is chirally broken and confining, and in the weak coupling it is actually deconfined with a Polyakov line non-zero. And then I conclude that that's what the phase diagram or phases of QCD.
No, because, well, this is not QCD. I mean, I have shown you that it is equivalent to QCD precisely if the Polyakov loops are traceless. Otherwise, there is no equivalence.
Okay, so the derivation requires, the equivalence requires that the Polyakov loops are traceless.
Yeah.
But then you have a system that decides to okay.
And then it's not equivalent to the original theory.
Okay.
So this is why there is a proposal by Neuberger and Narayanan that is called partial reduction, which tries to cure Gucci-Kawai reduction not by modifications of the original proposal, but by going to a larger than one lattice site box in such a way that the number of sites of that box brings you above lambda QCD, above the critical temperature, such that the traces of the Polyakov loops are guaranteed to be zero. So in that system, where you have by confinement, I mean, by being above lambda QCD with a small box, I mean, it's not small, it's a box of around 1 Fermi, say, no? But if you are with a box of around 1 Fermi, from that point on, in which you recover trace of Polyakov loop equal to 0, there are no more finite volume effects, and you can play the game, right? But this requires to be in the broken phase, so above the critical in a sense, and cannot be done on a single site lattice, unless it's very coarse. But then there is no continuum physics. I mean.
Then that's my ignorance. There is the quenched Eguchi-Kawai and the twisted Eguchi-Kawai.
Quenched and twisted, and then partial reduction of Neuberger and Narayanan.
The quenched doesn't work.
So quenched, Neuberger claims that he can solve it, and he has a paper in 2020 saying that he can also solve quenching, but there are no simulations proving it. So the problem with quenching is that, so typically what you do in quenching is you have these matrices and you diagonalize them, right? And then you have these angles in the diagonal. Well, you have another version to do this, but I think that, okay. So the way you do the simulations is that you freeze the angles and you simulate these matrices, okay? And then you average over the angles, preserving the good properties, right? The problem that was, I think it was a paper by Bringolds and Sharp, so we can ask also, because I don't know very well the details, but Steve will be here next week, and he knows it, right?
I ran into that paper during the lunch break, but I didn't have a chance to read it.
Yeah, how do you write this? I don't remember. Bringolds.
Z.
C, no?
Okay.
And Sharp. A T. Here?
I can't remember the
TZ, okay. And Sharp. Okay. And they argue that the problem is that when you simulate these things, they induce, there are matrices here that induce permutations of the angles. And this is enough to spoil the center symmetry property. I think this is the claim, but I'm not, I don't know very well that. Neuberger claims that what you have to do is freeze the permutations also. Don't include them in the partition function for the view muse, and then it goes.
And then the twisted Eguchi-Kawai?
Yeah, the twisted Eguchi-Kawai I'm going to explain now. The twisted Eguchi-Kawai.
If it interferes with
No, I can. So the twisted Eguchi-Kawai is the one-side box, but the problem appeared with periodic boundary conditions. And the twisted Eguchi-Kawai box is going to use twisted boundary conditions. That is something that I'm going to explain now. Okay, what are twisted boundary conditions? These were introduced by Hooft, I don't know, late 70s, 80s, late 70s. No? And these boundary conditions are very nice because if you do them in perturbation theory on a small box, they quantize momenta precisely as if they were living in an effective box of this size. So if you compute momenta in perturbation theory for the with twisted boundary conditions, the momenta is quantized in this way. So you get automatically in perturbation theory this thing, which is something that for the Eguchi-Kawai model was also done in perturbation theory using either the angles. This is what you did, Gross and Kitazawa paper. And in the tech, it was also done in the continuum by González Arroyo and Cortez-Altes, deriving the Feynman rules, where this appears. Okay.
Why haven't anyone tried to simulate the...
This one?
Yeah,
Well, the paper is 2 years ago,
that's Neuberger.
and it's Neuberger.
He's not part of a big lattice.
I don't know why it has not been picked up. So maybe, yeah, maybe they could, because, I mean, they have all the machinery to do this, so they could repeat the simulations in this way to see if it works or not. But as far as I know, it has not been done, but I'm not completely sure.
So is the problem that it freezes the permutation or that it moves the permutation?
He doesn't allow permutations of the angles while you are simulating these things.
Oh, I see.
And then a posteriori you average over
So then
everything.
you average over the permutations. So it's the problem. Okay, good.
You have to change the order of the
Yeah,
things.
makes sense, yes.
So let me discuss a little bit about these twisted boundary conditions, and then I'm going to the continuum, okay? So what I'm going to do is finite volume Jamils. I leave fermions out, okay? And this is this thing that talk started, as I say, in the late 70s. Which, by the way, is coming back because all these things that do generalized global symmetries involve, in some cases, putting twisted boundary conditions or using Toft fluxes. So this is all coming back again. But as I said in the morning, I'm the old bottle, so I know it's the old way. I don't know it the new way. So if there are experts in generalized global symmetries here, maybe you are? No.
I know a bit about the new bottle, the new wine, the old bottle.
So maybe you can help me to translate, because for me it's not very easy to translate. The languages are, very different, right? So this is part of, which also in some sense connects with Hamiltonian truncations that we have been listening about last week or 2 weeks ago, because this is also a way to, in some sense, truncate in a natural way the Hamiltonian. I mean, you put the theory in a small box, like this, and then due to asymptotic freedom, if the box is small, the theory is perturbative, okay? So the thing is that you have to run with L. If you have volume independence, you would argue that you run with L effective, but let's for the moment just have L. This is 0. Here you have lambda and Mills. And then in this region, the theory is perturbative. Okay? So the Hamiltonian can be diagonalized. I mean, you can do the diagonalization of the theory without any problem of truncation or gauge invariance or whatever, and you know how the states there are. So I will describe a little bit later how the states look here. Okay? And here you have confinement, which is the hard part, where you know that the Wilson loop has to have an area law, and you have to have that the loops that wind on the torus should decouple with string tension times the size of the box. Okay. So the idea, also late 70s, was to try to push the perturbative domain across until here. So, for instance, in the paper that Callandas and Gross where they discuss about fractionalization and instantons and merons and these kind of things, one of the statements is let semi-classics close the gap, right? So you have here perturbation theory. Somewhere below lambda jam nils, you will have semi-classics that will bring you a little bit further. And the hope was that pushing, you would get here, okay? This is a hope that has not really been realized, I must say. But there is a lot of lattice work investigating this transition and trying to extract information of how the transition takes place, okay? So here we have semi-classics. So on the lattice, also using continuum techniques in the 80s, there was a very long amount of works following the proposal of Toft to do these kind of things. And it was initiated by Marty Lusher, and then González Arroyo and collaborators, and also Pierre van Baal and collaborators. So if you haven't seen the PhD thesis of Pierre van Baal, I really recommend it, because it contains all this explained in a beautiful way, and many of the things that the people are doing in generalized global symmetries applied to Toft fluxes are already in some way there. Okay? So his thesis, I think, is really a good thing to look at. And it can be found on the internet. If you look for it, it can be found on the internet. Okay, so the idea is, to try to push this as much as possible. So what I'm going to do is now describe what are twisted boundary conditions and what are the states that in perturbation theory you find in the small box. Okay. So twisted boundary conditions is also what is used for tech, as I said. So the idea is the following, that is also very much related to these generalized global symmetries, is the fact that if you live on a box, this is not the plaquette, it's now a continuum torus of size L. Okay? If you live on a box, the physics, local gauge invariant quantities have to be periodic in the box. Okay? But this leaves some freedom to decide how the gauge fields transform, because they have to be periodic up to gauge transformations. Okay? So if you have the gauge field here, let me put a mu of x. This point here is identified with this one, but it doesn't have to be exactly equal. It can be equal up to a gauge transformation. So if you displace this field by L, I'm assuming the torus is symmetric, but you can do different sizes if you want. Then this is equal up to a gauge transformation that depends on the direction you shift. Like that. Right? And these are called the transition matrices. They basically define in which torus you are living. Okay? So there is a condition, a consistency condition that these matrices have to satisfy that have to do with the fact that if you move from here to here along this direction or along this direction, the result has to be the same. Okay? So from here to here you move, let me call this rho sigma, with gamma rho and gamma sigma, and in this way you move the other, gamma sigma, gamma rho. Okay? So they have to be identified, these gauge transformations have to be identified here, but the gauge field lives in the adjoint representation. So it is blind to the center of the gauge group, and then you don't have to impose that these two gauge transformations are the same, but it's the same up to an element of the center of the gauge group. Okay? So the condition is that omega rho x plus L sigma times omega sigma of x has to be equal to an element of the center of the group that I'm going to call rho sigma times omega sigma x plus L rho is this, okay? And this quantity has to be an element of the center, so it's something of the form exponential 2 pi I n rho sigma divided by n. Okay? And this number is what is called the twist tensor. Okay? And it's gauge invariant. You cannot change it by a gauge transformation, and this is what parameterizes the torus. And I think this is what is called the two-form background in the generalized symmetry argot. Okay? So, just as maybe here for tech. Tech is a particular choice of this twist that is taken in this way. You select this as well, epsilon mu nu is just 1 if mu larger than nu, minus 1 otherwise. And then you put here a number, and then you only take n's that are the square of an integer, and you put here dr. Okay? This is a particular choice that tech does for the boundary conditions. So the vacuum solutions for this kind of twist, if you write the Wilson action for this twist, it would look like sum of mu nu, and then you have identity. And one can show that one can make a transformation of fields such that the only thing that remains of this twist is the set factor that goes here multiplying the plaquette, right? So you put here set mu nu star times the plaquette. This is the form that tech takes when you impose the boundary conditions, okay? So if you look at the zero axiom solutions of this equation, they will satisfy u mu u nu, set mu nu, u nu u mu, which is a version of this consistency condition that I have here, okay? So these configurations that satisfy this and have action equal to 0 are called twist eaters. They eat the twist, okay, because they have zero action. And through these equations, you can easily see that the trace of these guys is 0. It's 0 if set mu nu is non-trivial, okay? So the vacuum configurations are not center elements. They are traceless objects. And you can construct any loops out of these traceless objects up to a square root of n, and they will still be traceless. Okay? So this is how tech escapes, in principle, the problem of spontaneous symmetry breaking. Okay? The original tech model had k equals to 1, and this is what fails. We will see why. Okay? So the trick to save tech is to scale k with n. Okay? In such a way that k over square root of n is kept fixed in the larger limit. So this would be the trick to rescue tech, but okay. This was just a parenthesis, okay? So these are the boundary conditions that were introduced by Toft, and then one can, using these boundary conditions, look at perturbation theory in the box and see how the physical states look like in this box. Okay? So I'm going to look now at the physical states in this box. And for that, I'm going to go to the 0 equals 0 gauge. Okay. And then I have the freedom still to perform gauge transformations that are time independent. Okay. So in principle, to be compatible with the boundary conditions, I'm on the 3 torus, and on the 3 torus, I can write the consistency conditions in this way. With constant matrices. For 3 of them, it's always possible to bring them to constant. And then the gauge transformations, to be consistent with the periodic boundary, with the boundary conditions that I have imposed, which are, I remind you, these ones have to satisfy this. When I shift,
Is it periodic in the zero direction?
The zero direction is infinite.
Or it's infinite?
So I'm like in the Hamiltonian formulation, okay, T3 times I.
Good, thank you.
So these are gauge transformations, but there is an additional set of transformations analogous to what we call large gauge transformations when we talk about instantons, that under the boundary conditions, under the displacements, are characterized by a set of integers, k, and then when you displace these matrices in a given direction, I for instance, they transform in the same way but with a phase, okay? That depends on this number. Okay? So this is very similar to what happens with the theta vacuum in QCD, in Jamils. Okay? So this set of matrices commute with Hamiltonian, and they can be simultaneously diagonalized. So there is a quantum number associated to the action of these onto the wave functions, right? So when you act with one of these matrices with index k, and also I'm going to put an instanton number, okay, there, on the wave function of physical states, I will characterize the wave function with the theta vacuum and also the something that is called the electric flux. And the transformation is exponential 2 pi I over n k dot E plus I nu theta acting over phi. Okay? So this works very similar to the instanton number and the theta, but now there is this discrete set of integers that characterize the states also. So this electric flux takes values in the integers mod n. Okay? So the Hamiltonian is decomposing in sectors characterized by the electric flux. The glue ball lives in electric flux sector 0, and the loops that wind around the torus have electric flux, the number of windings. Okay? So the free energy or the partition function for a generic electric the twist in the time direction is usually parameterized by something that is called them. In the time direction, no, in the space direction, and this is called the magnetic flux. Okay? So this is the partition function for you have in the same way as you sum over instanton numbers the set projected over a given instanton number, you have to sum over k with phases the sets with fixed k and fixed k. And this is what we simulate on the lattice. We can do it for tech, or we can do it on a standard lattice simulation, infinite, whatever, on a small torus or a bigger torus or whatever. Okay? So this is a standard lattice simulation with magnetic flux given by that, and k is equal to the 0i component of the twist tensor. Okay? So this is a way to simulate these twisted boundary conditions on the torus.
But now you're in Euclidean space time.
No, I'm in the Hamiltonian form. Well, when I go there, I will be in Euclidean. Yeah. For the set, I will be, in principle, I have not gone to, yeah. There, when I do the simulations, I will be in Euclidean, yes.
So how can you fix the gauge to A0 on this in the simulation?
No. This is not. This is continuum
But
physics.
I thought here you did simulation.
I don't need to fix the gauge here. In the simulations,
Oh,
I
you don't
compute.
fix the gauge at all.
You don't fix the gauge at all. Here in the simulations, I compute electric fluxes by computing Polyakov loop correlators. Okay.
Got it. Thank you.
So The electric flux is created by, if this is your torus and this is time, by loops that wind, the Polyakov loops that wind in the torus direction. This creates electric flux. And so if you compute a correlator of two electric fluxes at large time, it will give you the mass of the electric flux in the simulation, okay? And then the magnetic flux is generated by what is called the 't Hooft operator, okay, which is something that people have also measured on the lattice, but it's a complicated quantity because you have to compute the ratio of two partition functions, one with twist and the other one without twist. And this is very complicated, but I don't remember. Maybe in the 2000s or so, Massimo Delia and Philippe de Forclans looked at these things, at this ratio of partition functions, okay? Which is nice because, I mean, in the paper where 't Hooft introduced all these things, it's a very nice paper that I also recommend. There is something that is called an electric-magnetic duality, where using only the Euclidean properties of these things, he's able to show that if you assume that all electric fluxes condense at zeta equals 0, so they all become heavy, then it's guaranteed that all magnetic fluxes are light and condensed. And this is the confinement phase. Or vice versa. If all magnetic fluxes are heavy, all electric fluxes are light and condensed. So this is the two phases, Higgs and confinement, that a gauge theory in principle can have at zeta equals 0. And he shows it just by, well, okay, he's not proving anything in principle because he has to assume that electric fluxes are heavy. But he shows that one thing implies the other, which is a very nice paper. Okay. So if I go back here, I can compute in perturbation theory what is the energy of electric flux here. And here, in the confinement phase, I know that these windings have to grow linearly with the size of the box. Okay, so it will be a string tension times the size of the box, the energy of these guys. And in between, they have to be connected in some way. Okay. So one way to try to connect these things with when you have non-trivial boundary conditions is fractional instantons. These boundary conditions a la 't Hooft are very particular because they allow for fractional charge. Okay? So if you, which is very nice. So if you look at the topological charge with these boundary conditions, you can derive a formula that tells you that the topological charge looks like that. This is an integer, like the instanton, and then there is this term here. So if the numerator k dot m is different from 0 mod n, you have fractional charge objects. Okay. So in principle, you may have q equals 1 over n. But solutions of this sort are very rare. Analytic solutions also are only known, they were originally written by 't Hooft also, and they are only known for very specific torus sizes. So they are only self-dual if the torus size has a very specific size. And yes, I say these solutions were first obtained by 't Hooft. There is a generalization by González Arroyo of these solutions of 't Hooft, but again, only for certain ratios of the torus sizes. And this generalization has been recently used by Popitz and Amber, which I think is nice. To compute the Gluino condensate in n equals 1 super-Young Mills. So there is, so in n equals 1, the condensate of Gluinos is different from 0, okay? And doing this calculation without the fractional instantons in principle is a problem because you cannot saturate this two-point function with 0 modes of an ordinary instanton. So what people typically do is saturate with the instanton the n-point function, assume clustering and get the other one, or other techniques. There are two techniques. One is called strong coupling, one is called weak coupling, and they don't agree. Okay. So in this case, you can saturate directly the gluino condensate with the fractional instantons, and they get a number that is compatible with the weak coupling calculation, which is nice. Okay. So I'm not going to talk more about fractional instantons. Just these are preferred guys for making confinement of Tony González Arroyo, and he has worked on these things for a lot of time. There is also now some attempts to use these guys for semi-classics in T2 times R2. Tony with Werner and student of Werner are working on that, but also Michael Tunsal and Tanizaki. There's quite a number of people in the HepPH community looking at semi-classics with these things. Okay?
So this new result validates one of the two
the weak coupling, yeah, the weak coupling, yeah.
Didn't Ciano do one of those?
He was, Arkady is not here now, but I think he's, Schiffman, Jankielovi, no, Sigma, the SNBZ, Novikov, Weinstein, and Sakharov. Schiffman, Novikov, Weinstein, they did the two.
Okay.
So in one case, you use the endpoint function and saturate with an ordinary instanton, and then use clustering to.
Yeah. So is that the one that's okay, or is that?
That's the one that is wrong.
That's the one that's wrong. Okay.
Indeed,
So do people think they know what happened?
Well, there were some papers by I think it's Jose, in the. There were some papers that claim that this fails because there are contributions, like these fractional instantons, and there were some papers also in the 2000s using monopole constituents of instantons that saturate the bound in different ways. And then if you neglect part of the configurations that contribute to the endpoint function, the result is not correct. So I think this is the way they understand the failure, in a sense. We have done the calculation also on the lattice using TEC. And this is what Claudio Bonanno will talk about in March. And we also get the weak coupling, consistency with the weak coupling result, and the independence of the weak coupling result, because they have different end dependencies, the two quantities, the two determinations. So you can disentangle by the end dependence which one agrees with you. Okay.
But you should tell you that, the fractional instances are essential if you want to get such configurations in the large end.
If you want to get
any contribution for the large end.
Of course, I didn't say that, but you're right, thanks. So there is this argument that these functions are irrelevant in the large end limit because basically this is the action of an instant. This is the contribution of an instanton to the path integral, okay? But if you go to the large end limit, you have to put an n here and then an n here. So the contribution of one instanton to the path integral at large n is suppressed. Okay, so standard instantons would not contribute. One could argue here limits and things like that. Okay.
There are different cases where it certainly fails for these fractional instantons.
Yeah, for the fractional instantons it doesn't fail because you have the q here, which is 1 over n, and then it's precisely what you need. So for fractional instantons, the scaling would be precisely like this. Okay.
There are other cases where this argument can fail. The prefactor can grow like a power event.
Okay. So which cases would be that?
For example, the simplest case where you can work out things exactly is large n, it's two-dimensional QCD.
Okay.
Where there's instant and there's large n phase transition. When you go to consider QCD of the sphere as a function of the radius of the sphere, there's a phase transition from sort of confining phase to crazy phase.
So who is? I'm not aware of those.
This was first noticed by Kazakov and Douglas, and interpreted. Right, you can calculate exactly pretty much what you see. But Lattice and I showed that it's really a instant-induced phase transition
Okay.
as a function of the radius. At some point, this e to the minus n is compensated for by g to the n. There are lots of zero ones,
Okay.
a lot of three-factor movement, and
Okay.
a great example. And there are other examples.
Yeah, so in principle there are arguments to say that these guys can be...
Yeah, and the moduli space of instantons really looks like, if you
Yeah.
medical literature, like n objects.
Yeah. N separate objects. Yeah. There is also this argument that the moduli space of instantons precisely corresponds to having fractionals of...
Exactly, very specific.
and the location gives you the moduli, yeah. So what I'm going to do now is work out an example that we, on T2 times R, that we have worked out on the lattice. We have analyzed on the lattice and analytically. There are no semi-classics in this game, just perturbation theory and confinement. But it will help me explain why the original version of TEC failed and how to cure it, maybe. And well, I like the example because it brings the golden ratio in the game in a nice way, very peculiar, that is fun. Okay, so let me describe that. And let me say that in all this game, the lattice is very important because we don't know really how to cross. So we need to do simulations to really know what is going on there. Otherwise, it's just speculative, right? You need to check that these things really work. So you can do hand waving. Once I get to lambda QCD, this and this and this happens, but this is just hand waving. You need to do it. Because it's not simple. Typically these objects, for instance, the fractional instantons or whatever, when you get here, the gas of these objects is so dense that it's impossible to treat it analytically. It's not even clear if semi-classics is working anymore. So it's very difficult. So I think it's a good example of cases where lattice and continuum physics play together in a very good way. So let me do this T2 times R. Let me check my notes because I don't... which is a much simpler case, no? So basically in this case I only would have two matrices, gamma 1 and gamma 2, that satisfy these twisted boundary conditions with phase. This end will be the magnetic flux, okay? So if you want to solve the perturbation theory, you have to impose to the gauge field the boundary conditions, okay? And then there is a nice way to do a Fourier expansion that preserves these boundary conditions, which is very simple. And this is something that was done originally in the context of TEC also, where you have momenta, as usual. Then you have a number that depends on the momenta. This is not a matrix, it's just a number. So, by the way, here, these are in the Lie algebra. And then you have some matrices that depend on the momenta, okay? And there are n squared of those that form the algebra of the Lie algebra, a basis for the Lie algebra. One of them has trace, and that one has to be dropped from the summation. This is why I put this prime here, okay? So in principle, if you impose the boundary conditions to these things, you can extract...
So what happened to the color index?
The color index is here. This is a matrix n by n. Okay? So this is analogous to the matrices in tech that contain the information about the space they are entangled in the momenta. Okay. So this matrix can be constructed out of this gamma 1 and gamma 2 in a very simple form. Where m bar is the modular invariant, the inverse of m. Right? And n is an integer that is related to the momenta in this way, 2 pi over n. And here, NL appears. Okay? So the quantization in terms of the effective size is directly appearing here in perturbation theory. Okay? Moreover, here, momenta equal to 0 in all directions or 0 mod n is not permitted because this would make this matrix have a trace. So it's not included in the sum. Okay? So n is different from 0 mod n. There is no 0 momenta, and this implies that there is a gap in the spectrum of the theory. Okay? The theory has a gap, and indeed, if you measure the energy of electric flux, is directly given by the momenta of electric flux. The one gluon you can interpret as, well, the Polyakov loop is one gluon winding around the box. And then you have this momenta here, which is different from 0, I said. So actually, let me introduce, well, in this theory, the coupling has dimensions, okay? It's dimensionful because we are in 2 plus 1 dimensions. And then I will introduce a dimensionless variable that contains lambda, L, and M, like this, okay? So the energy of electric flux can be written as 2 pi n units of lambda divided by this x. Okay? At leading order in perturbation theory. Okay? So if you go back to this plot, now I don't have this anymore. In this region, the electric fluxes come from above and go down with x. So let me do it again. I'm going to write it to draw it again. So you have x here, 0. Okay. This is the perturbative region, and this is the confinement region. So the electric fluxes, if I plot here, I'm going to plot the square of the energy of electric flux over lambda squared. It's coming like this, in this region, okay, in perturbation theory, because it would go like 1 over x squared. And here, since I have confinement, these energies will go like the string tension of electric flux times L. And I'm going to put again lambda. I put the string tension in dimensionless units. And then I have here lambda, and I put an n here. And this is x, okay? So these grow like x. So here I have this. Okay? So now the question is what happens in between.
The plotted here is squared, no?
Yeah, so it's x squared, sorry. Yeah, it's not linear. It should be something like this. And also here is 1 over x squared. Okay?
This is a logarithmic perturbative potential.
Yeah. So in principle, one can try to push the perturbative calculation further, and here is where the problems appear. Okay? So if you push the perturbative calculation further and you compute this energy squared, you have the 2 pi n over x, and the first loop correction, which is the self-energy of the gluon, is negative. So you have a function that depends on the electric flux times x, times 1 over x, sorry. Negative.
This is E now, not E squared.
Sorry? Yes, okay. So G is a function that we have computed analytically, but I'm not going to write it. The only thing that matters is that G of Z goes like 1 over Z, for Z going to 0, where this is the distance to the closest integer. Okay? So you see immediately here that if I take n to infinity, some electric fluxes will have a G that diverges, and I have a negative number here. Okay, so I go like this. And this is what is called, is in E squared a tachyonic singularity. Okay? Instability, sorry. And spoils perturbation theory. Okay? I can write the E in terms of the magnetic flux, because there is a relation between magnetic flux and the electric flux through the momenta. So this is basically m bar times the momenta over n. So you can see here that for low momenta, this will happen if I keep the magnetic flux fixed when I send n to infinity. Okay? This immediately breaks down. So this is the first cure that one has to do to take. I mean, you cannot keep the flux fixed when you take n to infinity, because these things enter the game and spoil everything. What happens in this case? I mean,
G was the what loop? Pascal G was the one loop calculation?
Yeah, this is the self-energy of the gluon in the box, computed at one loop.
So what happens at 2 loops?
I don't know. I didn't compute that.
Well, if it's positive, it might rescue.
Of course, but yeah, it might, and it might go like this, okay? Also because the confining part is pushing up. But the lattice simulations show I mean, we have done lattice simulations for many values of the flux, for many values of the electric energy and so on, or for many values of n and electric flux, and we see that the electric fluxes get light if you don't choose the flux, okay? So, in principle, you may have here a phase transition to a place where the electric fluxes become light and condense, and then you break continuity from the perturbative domain to the confinement domain. By the way, this continuity here is what is called, in some cases, adiabatic continuity or this kind of thing. So it can be broken due to these tachyonic instabilities in some cases. These tachyonic instabilities are not a surprise, because these theories with twisted boundary conditions are equivalent to non-commutative gauge theories. This is just a sort of parenthesis. And I think it's well known that in non-commutative gauge theories at one loop there are tachyonic instabilities. So this is a reflection of that. And there is an old paper by Guralnik, Steiner and Lopez, that discusses this issue precisely, also related to twisted boundary conditions and electric fluxes and this kind of things. Okay, so the question is it possible to select a twist such that you avoid completely these kind of things? And this is basically the question. I mean, you have to sort of rescue the thing. So here I go to the lattice results and empirical things, okay? We cannot do it analytically. But the observation that we have done is that all our numerical data are fitted rather well, even at a quantitative level, with this formula. E squared equals to the one loop quantity plus the Nambu-Goto action, okay? Which contains the string plus the correction that gives rise to the Lucier term, okay? For the lattice people. So this is fitting rather well the numbers that we have. So the condition for the avoidance of these instabilities will be that for all electric fluxes and for all x, we keep this quantity bigger than 0. Okay? And here is where the golden ratio appears in a magical way. Very difficult. Well, okay. So this condition can be translated in a condition for the fluxes. I have to copy, but I don't remember. Which is that this thing is defined as mean when E and N are coprime numbers of E and E over N. This number has to be larger than 0.1. You can write it also in terms of the M bar and the momenta.
That first line, Z-min, what is Z-min?
This condition can be translated in this quantity being larger than 0.1.
This quantity is defined as the minimum over
With N over E, coprime with N. E, the distance to the closest integer defined by the magnetic flux, electric flux, and N. Okay, this condition.
greater than 0.1.
Z, approx. Okay.
That's
0.1. Okay. So, these centers, well, the 0.1 comes from, I don't know, inserting the string tension, measure on the lattice, blah, blah. It's an empirical condition, okay?
But it means that M has to grow as
N. Yeah. Also, you can write it using that E is related to M bar, the momenta, like the momenta, M bar, N over N. Okay? This way.
And if that's not satisfied, then there's the
Then you go below 0. Then you go below 0 and you enter here. Okay? So this condition has been analyzed in a paper by González Arroyo and Chamizo, who is a mathematician. And they find that it's equivalent to a conjecture in mathematics that is unsolved, that is called Zaremba's conjecture. So the question is the following. For any n, is there a M that avoids the instabilities? You choose an n. Can you find a flux that avoids the instabilities? This is called the Zaremba's conjecture. And it's unsolved. But what is known by a mathematician that is called 1. Sorry?
M is an integer that could run up to N, right?
Yes, that's right.
So why is it, I mean, can't you always find this?
No.
Right.
Well, imagine that n goes to infinity.
Set M equals N.
Sorry?
Set M equals N.
If you set, no, but it has to be, if you set m equals n, tech fails because it's equivalent to periodic boundary conditions.
N minus 1.
Well, M must be high, right?
N minus 1 is also not good because the 1 over n, then it will be this. The n is irrelevant. I have to look at the distance to the 0, and what matters is n over n. Actually, no fraction, well, the limit does it, which is peculiar, okay?
But you want n to be near a half of big N or something.
Wow.
So, I mean, for n finite, you can have solutions because there are mathematicians that say that for almost all values of n, you can find m's that satisfy the condition. The problem is when you send n to infinity, then you are cooked, in a sense, because not cooked, but okay.
Okay, you said for almost any n.
For almost any n,
Not for arbitrary n.
No.
And if you go to infinity, you have to go through the arbitrary ones.
if you go to infinity, this is what I'm going to discuss, okay? So what happens if you go with n to infinity, okay? If you go with n to infinity, let me first do an interlude with this non-commutative because it's going to be useful for that also, theories. So these theories are equivalent to non-commutative gauge theories with a non-commutativity parameter that is determined by dimensionless if I take the dimensionless by m bar over n. Okay? This is something that can be derived through the Feynman rules of these things. So if you look at this momentum expansion that I erased, and you compute the structure constants with these matrices that depend on the momenta, you get that the structure constants are replaced by things that depend on the momenta in the vertices. And this is precisely what defines a non-commutative gauge theory. Okay? And this is something that was seen already in the very old times of tech, was seen that. And then there is something that is called the Morita duality, that also tells you how to relate these things, okay? So the fact that it's, well, okay, it doesn't matter. But this is the non-commutativity parameter associated to the non-commutative gauge theories that are related to these guys.
Normally in a non-commutative theory, there's a direction, is it what, space non-commutativity or space-time?
Space non-commutativity.
That's unitary.
Space-time non-commutativity is an issue, yeah.
If it's a non-zero space-space.
No, this is, so the phases are like pi, pj with this in the two torus. It's non-commutativity in the two torus. Non-commutativity.
It's a non-pathological magnitude.
Non-commutativity in the two torus, yeah. Yeah.
Right, that's very cool. But you broken.
Yes.
Sure.
Okay.
So,
so the question also affects this, because in principle these twisted boundary conditions and were used also in the old times by Amjon and company to simulate non-perturbatively non-commutative field theories. Okay? So these are the non-perturbative regulators of the non-commutative field theory, if you want to put them on the lattice. So the question is, if I send them to infinity, can I reach any value of the non-commutative parameter, even an irrational number? No? So there is so also a long time ago, I mean all these things a long time ago, something called the singular larger limit, in which Alvarez Gaume and Barbon proposed, which is, we have this L effective, which is L times N, okay? So I'm going to send L to 0, N to infinity, keeping L effective fixed, okay? And this is the game I would have to play, for instance, at large N to run here. The theory is non-commutative all the way, right? At infinite volume, we expect to recover the normal physics, but all the way is it's a non-commutative gauge theory, which is equivalent to the twisted thing, okay? So, and then you have a sequence of these things that tend to the non-commutativity parameter. So, is it possible to choose to reach in this way any value of these irrational values of this? And this is another question that the mathematicians have analyzed, and the answer is no. In general, no. Only for a zero measure set of values, and the optimal one, the optimal set, which saturates this bound, saturates the bound, which gives a maximal value to the set mean, is the Fibonacci's. That's how the golden ratio applies. So you have to choose m over n equals to the Fibonacci in the position I minus 2 over the Fibonacci in the position I. Okay? Magic, right? So with this, you avoid fully the instabilities, and you reach a value of the non-commutativity parameter that has to do with the golden ratio, and is 3 minus the square root of 5 over 2. Okay? This is a particular case. There are others, but any fraction fails. Okay? If you want to.
But this is still just one loop.
This is one loop plus Nambu-Goto.
Okay.
Yeah, which describes the data quite well.
Yeah.
Yeah, quite well. Yeah. So we have simulated the Fibonacci, and we have seen no evidences of tachyonic instabilities or these kind of things. So, but we cannot go to very large n's. I mean, in this game. So I don't know.
Trying to answer you.
With this, we can go up to 30-something. Tech is better, because tech goes with the square root of n. And then in tech, González, Arroyo, and Naukawa have gone to 30-100. I mean, yeah. No, not 30, 13.
13.
So I think 37, I mean, they have to be primes squared. So 37 is prime? I don't know. Squared. This is the biggest they have done, I think. For computing the string tension, pure jam mills. In the case of computing mesons, we have gone up to 800 something to do tech. Okay. So I finish just with one thing about the Fibonacci's, which is also very peculiar. If you do this plot for the Fibonacci's, okay, you plot the energy of electric flux over lambda squared. You avoid the instabilities, and what is curious is that if you compute the minima value, the minimal value is obtained when the electric flux is itself a Fibonacci, and then you get a sequence for large n of things that go like this. Okay. Basically, all minima the same, and if you trace this. This is very close to the infinite volume global value that Tepper has computed.
So how large does n have to be large n here?
Here.
Yeah, like what values of n? Because you
So-
were saying your n's are not large.
Well, we have gone up to 34. Using the formula, I can draw this for any n that you want. So I use if you use Fibonacci, I don't know, 1,000 or whatever. You
So
can.
is 34 not large n?
I don't know. I don't know. The corrections I cannot compute. Okay, in principle. Well, in these theories, it's infinite, so I could compute.
Yeah, but if you look at the
could compute them.
independence and
The independence is not very strong because precisely everything is controlled by this factor. So in a sense, small n and large n are equivalent in this setup, okay? Because if it were true that everything depends on L effective, it doesn't matter that L is small, that n is small, as far as L effective is the same for the two theories, okay? So in principle, this is the idea of another reflection of the idea of volume independence. Different theories with different n's behave in a similar way, combined in this way. Okay? So it doesn't matter so much whether n is finite or not. It matters for the appearance of these instabilities, because they appear at n finite. You can have maybe one flux that goes down, but not generically. Okay? But at n infinity, generically, some flux will go down. So yeah, this is just a curiosity, which is surprising, but okay. This is it.
So this theta is large in this limit, or?
This one for the Fibonacci is 3 minus the square root of 5 over 2.
So does that mean that the T2, it's not very close to rotation?
Yeah, the
And is this
non-commutativity is there.
Computed in a commutative, in a theory that's supposed to have this rotational invariance?
The box breaks the rotational invariance anyway.
It breaks it down
So-
to a discrete one.
Yes,
But
yes. So what
is the
happens in
discrete
this?
behavior the same in both cases, or is?
The two theories in principle are equivalent, yeah. So this is, when you have this rational theta, the gauge theory with rational theta, the non-commutative theory with a rational theta is exactly equivalent to one of these theories with twisted boundary conditions. This is the claim of this Morita theory. So in principle, you can simulate one or the other, and it is the same. When it becomes irrational, not, of course. You have to do a kind of game like this, but if the theta is rational,
Based on taking the periodicity longer until it
I don't really
comes
know.
back, or?
I don't know. I don't really know. Yeah, I don't know. But what happens with the non-commutativity parameter when you look at the large N limit is that you have two pieces. Planar diagrams don't depend on theta, and non-planar diagrams depend on theta. Okay, so these limits, the singular large N limits, if you take them here in this way, they are not Toft-like. I mean, you don't kill the non-planar diagrams, you preserve them because there is a theta dependence in the game. So planar diagrams are not dying out. I mean, it's a non-commutative theory. Okay, so it's a different limit. The only thing is that you expect that when you go to very large X, you recover the standard theory. It should be, because this is just a gauge theory on a box, and at infinite volume, everything should be independent of the boundary conditions of the box, right? If there is confinement. So, okay, so this was just to do a case which can be done to some extent analytically and also numerically, and brings back things that are sort of interesting. Right? I think this. Okay.
So do you think you can do this for T3?
T3, you first have to choose the twist appropriately, which is not obvious what to do in T3. It would be very interesting to do it for T3. Yeah. So
multiple pairs of these integers.
In T3 you have.
Twists are characterized by pairs of directions, I guess.
Yeah, you would have. In that case, you have three M's.
Yeah.
A vector of 3 M's. And then, I mean, I did it many years ago for SU2, but not very many years, I mean, a lot of time ago for SU2. But it could be done, yeah. It could be done. In principle, it could be done. Now, a lot people is studying T2 times R2. There, the fractional instantons look like vortices, and they are trying to do the game with the vortices in T2 times R2. So there are numerical simulations being done in that case. Not involved, but.
Other questions from Margarita?
How do you come across the Fibonacci's?
How do you come
across Fibonacci's?
It was not me. This was the Tony with this mathematician, Chamizo. Yeah. So we got this numerically, and we knew that this imposed a condition for the fluxes, but we were solving it case by case on a poor woman's basis. Okay. But then Tony talked to Chamizo, and they worked it out together. And I mean, number theory is world, no? So they came out with all these things, which is I don't know, Fibonacci's pop out everywhere, also here, which is very surprising.
So you have T2 times R, but then you say you do it numerically.
Well, yeah, okay.
So
R is
so the time direction is just super long, and
Yeah.
standing stuff.
Yeah. So I don't know. We did 100 and whatever in the time direction, and
Okay, so if people did T2 times R2, they would have two directions small and two directions.
two very large. Yeah. In principle, if this is true, the two small directions are also large in some case.
Yeah.
And for instance, this we have used with Alberto Ramos to do the running of the alpha in Fourier mills, because the boxes can be sort of symmetric even if they are not, if the twist forces them to be larger. So we have this worked with this scheme that uses twisted boundary conditions and allows you to enlarge artificially the box. Okay.
This morning you mentioned doing glue balls on R cross T3.
No, I mean, here we computed the glue ball also. We get.
That's in 3 dimensions, yeah.
This is in 3 dimensions. We computed and we get the number of.
But you think you could do that in general in R cross T3?
If n is finite, yes. In a finite box with n finite, yes, you can do. The problem is with the tech model to do
Oh, I see. You
blue
can do
balls.
the tech model, but you can just do different ends. Okay.
I can do different ends and volumes, normal volumes.
Nobody knows how to do the tech model.
Yeah. I mean, the tech model gives you a single trace easily. Double trace, it's an open problem, I would say. Okay.
Let's start Margarita.
Thanks.